A warehouse tour today. We'll start with the relational model blueprint, then look at core SQL operations, move into asking questions with queries, check out connecting data using joins, and finally, automating defense with triggers.
All right, starting with section 1, the relational model blueprint, establishing the floor plan. So, before we can store even a single piece of data, we need absolute strict rules. Otherwise, our warehouse just becomes a giant dumping ground, right? The relational data model is basically the ultimate foundation of our warehouse. It dictates that all data must be organized neatly into tables consisting of rows and columns. But listen, it's not just a fancy spreadsheet, it is backed by rigorous mathematics. Completely invisible to the naked eye, theoretical frameworks like relational algebra and tuple and domain relational calculus are actually running the show. These are the mathematical blueprints ensuring every single data point can be logically defined, manipulated, and retrieved. You don't necessarily see the algebra when you're writing code, but it is literally the physics engine of our digital warehouse. It's what's holding the walls up. Now, to prevent absolute chaos on that warehouse floor, we have to enforce strict safety regulations. We call these integrity constraints. Take entity integrity, for example. Every item needs a unique ID barcode, a primary key, and it absolutely cannot be blank. No mystery boxes allowed. Then there's referential integrity. This acts like our tracking system. It ensures that if a box says it belongs in aisle 5, well, aisle 5 must actually exist. It safely connects our tables using foreign keys. And finally, domain constraints act as our quality control. If a shelf is designated for whole numbers only, you cannot stick text or a date in there. Together, these constraints are what maintain the absolute integrity of our relational model. Moving right along to section 2. Core SQL operations explained, the forklift operators. Okay, so our warehouse is built, the rules are set, now it's time to bring in the tools that actually do the heavy lifting. To run operations, we use structured query language, or SQL, and SQL relies on a few physical structural elements to get the job done. Think of tables as your heavy-duty storage racks, where the raw inventory actually lives. Views are like custom windows into those racks. Maybe the marketing team only needs to see product names, not the underlying cost data, so we just give them a specific view. Indexes are your speedy lookup catalogs. Instead of making a worker walk every single aisle to find a product, the index tells the forklift exactly which shelf to go to instantly. And SQL operators? Those are the logic tools we use to say things like, hey, find me items greater than this price or less than this weight. So the really crucial point here is how SQL manages the actual life cycle of data within this structure. Think about these 3 daily steps. Step 1. The insert operation. A delivery truck arrives at the loading dock, and we use insert to place a brand new row of data right onto our table racks. Step 2. The update operation. Let's say the price of an item changes or a customer moves to a new address. We don't throw the whole box away, we just use update to slap a new label on it. Step 3. The delete operation. The product is discontinued or the inventory is shipped out. Delete safely removes that row from our warehouse. These 3 commands, insert, update, delete, they manage the day-to-day operation seamlessly while strictly obeying all those integrity constraints we talked about a minute ago. On to section 3, asking questions with queries, finding the needle in the haystack. Let's be real. Storage is completely useless if you can't retrieve what you stored. It's a serious question. When your database scales to millions or even billions of rows, how do you find exact inventory inside a massive digital warehouse? The answer is SQL queries, and specifically subqueries. A standard query is basically like asking a worker to go grab all the blue boxes. But a subquery, that allows you to ask multi-layered questions. You can say, first, find out what the best-selling item was last month, and then go grab all the boxes that match that item. It's literally a query nested inside another query, giving you this laser-focused precision to navigate a fully stocked system. But retrieval isn't just about finding single items. Sometimes you need the big picture, right? That's where aggregate functions in SQL come into play. These are your commands like sum, count, average, maximum, and minimum. Instead of returning a million individual rows of raw sales data, an aggregate function just crushes all that data down instantly. It can tell you the total sum of sales for the electronics department, the average price of a textbook, or the highest salary in the whole company. It's basically the ultimate executive dashboard tool for summarizing vast amounts of warehouse data on the fly. All right, section 4. Connecting data using joins, the assembly line. In the real world, data is rarely stored in one massive clunky table. That would be a mess. It's separated for efficiency. Think about customer data. Names, contact info, their unique IDs, that lives completely separate from order data, which holds order numbers, purchase amounts, and the ID of the customer who bought it. In a well-designed relational model, this info is intentionally fragmented. Why? Because it avoids repeating the customer's name over and over again every single time they buy something, which saves a massive amount of warehouse space. But when we actually need to generate an invoice for them, we have a problem. How do we read it if the data is in two different places?
Well, this is exactly where joins come to the rescue, acting as our automated assembly line. A join operation seamlessly matches the customer ID from the customer data with the customer ID from the order data, stitching them together into one clear, perfectly usable view. Boom, we can instantly see that Alice bought a $500 order. It merges disparate tables temporarily, just for our query, without duplicating any storage on the actual warehouse floor. It really is the absolute magic of the relational database model in action.
And finally, Section 5. Automating defense with triggers, the automated security system.
So, we have our rules, our forklift operations, and our assembly lines. But how do we enforce all of this automatically? Enter triggers and procedures, which are often written in SQL or PL/SQL. A trigger is exactly what it sounds like. It's an automated security guard that waits for a specific event to happen, and when it does, it fires off a pre-written script. Imagine a rule that says, hey, if someone tries to delete a customer record, automatically save a backup copy into an archive table first. The user doesn't even have to remember to do it. The database just handles it automatically when the delete command is attempted. Similarly, procedures are these saved batches of SQL code that you can execute with just a single command to perform complex, multi-step warehouse tasks. They maintain absolute consistency without needing constant human oversight.
As we wrap up, I want you to consider this fundamental principle. SQL commands and integrity constraints work in perfect symbiosis. The commands do the heavy lifting while the rules prevent the warehouse from collapsing. Honestly, that is the core takeaway of our entire explainer today. Everything we've discussed, the mathematical relational model, the insert, update, and delete commands, the precision of queries and joins, and the automation of triggers, none of these are isolated tools. They are an interconnected ecosystem designed to seamlessly manage complex operations while ruthlessly defending the integrity of the data.
So, I want to leave you with a final thought to ponder. We've seen just how incredibly powerful basic automation is within a relational model. But as databases become increasingly autonomous, infused with machine learning and AI, what new intelligent triggers will shape the future of our digital warehouses? Will the database of tomorrow not just enforce rules, but actually predict them? It is a truly fascinating frontier for database engineering. Thank you so much for joining me on this tour. Keep asking those big questions, and I'll catch you in the next explainer.